Hello everyone, welcome to another one of my Leetcode videos. In this one we will do today's daily challenge, Leetcode 2246, longest path with different adjacent characters. So basically again we're given a tree, connected undirected graph that has no cycles with a root of 0. And we basically in this tree need to find the longest path where there are no two adjacent nodes with the same character. So for example, in this one, the path will be 0, 1, 3, because we can't go here, that's A and A, these are the same. Over here, it's only two characters, and we can't go here either because it's B and B. So the longest path where no two consecutive characters are the same is A, B, C. So 0, 1, 3. And the size of this is 3, so we output 3. And another example, I'll spend some time going through examples because there are some edge cases which we need to cover for this question. So going through this other example, we have again here a node with 3 children. So in this case, it can't be CAA because A and A will have two adjacent characters. So in this case, the path is going to be CAB. So notice how the path goes this way. Now imagine in this case, if we had this as the subtree of another tree up here, let's say this was 0, and let's say this was some other number like 5, since our root can always be 0. And here, let's say you had a letter A, and then here, let's say we had another node with B, right? Now in this case, we can't combine these two because this is A and A, but that doesn't mean the longest path is AB, because in here, if you look CAB, this is the longest path. So basically what I'm trying to demonstrate with this example is the longest path doesn't have to pass by the root. For this subtree, the longest path could be inside one of its subtrees, where here we have a path of 3, right? So here we could only get a path of 2. So in this case, the longest path is going to be 3, CAB. Let's now jump into our approach on how we can solve this Leetcode hard problem. So again, this is a tree problem, right? So we'll definitely use some kind of DFS and recursion, but what will we actually need for the DFS or recursion? So let's say we have, again, a bunch of nodes here. Now we need to define what value do we actually need from each node, right? So if you look at the parent node, what we want to be able to know is, can I actually go here, right? Can I actually go here, and can I actually go here? So how do we know if I can go here? We just compare the letters, right? So if the letters are the same, then we can't go there. If the letters are different, then that means we can go there, right? So that's all we need to compare. But then let's say we determine that the letters are different and we can go there. So what we need to know is the maximum path that this node has to any of its, child subtrees, right? So that we can add that path to the one on the root, right? So that would be the maximum path of this node, right? So we need to know here, what's the maximum path that this guy can go to any of its children, right? And then this is just how do we get the aggregated maximum path at any node. But then at every node, once we are at that node, we need to test, okay, what is a candidate path that we can compare. So if you notice, if we have a node and we have several subtrees, we can actually go in any of the subtrees, come back to the node, and then go down, right? So like, for example, if you noticed here, like in this node, we went down and then we came back down here. So it's like it's traversing 2 children, right? So you can go visit a child subtree, come back and go to the node. So we basically need the 2 children here which have the highest path among all the children, right? And combining those 2 children paths plus 1, because we pass through the root node, and obviously these are only the children that differ, right? For the children that are the same, we can't use them when we are looking for the 2 highest children, right? So that number will be our candidate path, and for every child what we need to know is the max path passing through that child, and then for every node we'll compute this candidate number and then aggregate it against the global maximum and see which candidate number is the maximum across all the nodes, and that will be our maximum path. So I know this is a bit confusing, but let's write the code and it'll get things a bit cleared up. So let's go into the coding. So luckily in this problem, we're given the parent. So we know which is the child and which is the parent. Given that we're given the parents, what we need is to be able to efficiently go from the parent to the child. So we need to build a reverse mapping from the parent to the list of its children. So let's do that first. So I've gone ahead and done that. So here we initialize our map node to children as a new map. And then we know that the parent of 0 is -1 because that's the root. So we skip 0, we start from child equals 1, right, up to the parent length. So this is kind of the index of the array. And we're given that the parent is the parent array of the child index, right? So then we just add this to our map. So if it's not already there, we add a new linked list. And then on the linked list, we get the existing linked list and add child to that list. Then after we've done this, we just need to kind of call our recursive function that will actually do the recursive DFS. So I've gone ahead and written this function where we take in the index of the node we're interested in. We pass in this map of node to children, and we pass in our string s, which contains the letters of each node. Now remember in our drawing earlier, for each node, it's not just the max path that we want to know. We actually want to know the max path passing through that node, right? And then also we want to keep track of the max so far so we can aggregate all the candidate maxes and then return the final max, right? So for each node, since this is a recursive function, this int return is not enough. We need two values. We need the max value that passes through that root so that we can use that to determine things for the parent. And then we need the overall max because the max could be in one of the child subtrees and not even pass through the root, right? So we need to keep track of our overall max. So let me go ahead and update the return types. So I've gone ahead and updated the return type. Instead of int, I return a node info, which will give us two values, the max so far and the max through the root. And obviously we just have a constructor here, and what we'll return from our parent function is the max, right? Because that's the overall max that we need. Now let's just go ahead and write this code. So if you remember from the example earlier, we need to keep track of the two highest children, right? Because that's what we'll use to create our candidate. So we have int max child, and we'll have int second max child. Next, we'll also have to keep track of our overall max so far. This is the overall max as our DFS has progressed. And I'll use a value of 1 here because the max you can have is actually just the node itself. We'll initialize that to 1. So now that we have these three variables, let's just loop through all of the children so we can compute our required variables. So I've gone ahead and created a loop that loops through all the children of the node. And we do a get or default because if that node has no children, it'll just return an empty list and we'll just not go in the loop, right? In which case these will remain our values, right? So now before we write the code in the loop, let's just write what we'll do afterwards, right? So we can work backwards. So ultimately we want to return new node info, right? And inside our node info, we want to provide a max and a max that's through the root. So the max is going to be the overall max, right? So let's just plug that in. And then the max through root, we'll compute it here. This will be used for computing paths of the parent, right? So this will just be 1 plus max child. Now, why won't it be 1 plus max child plus second max child, you might think, right? Because if it's the max through the root, we can go both ways, right? You must be thinking, but this max through root is actually used to compute the path of the parent, right? So we can't go up and come down and then also include the parent, right? So this is the max through root that the parent should be able to visit, right? So if the parent is visiting this from up, we can't actually go both ways. We can only pick one way, right? But the max that includes the two highest ones is going to be our candidate. So at the end of the loop, what we'll do is our overall max will be equal to math.max of the existing overall max. This will aggregate all the maxes that we see from the children. And here what we'll do is 1 plus max child plus second max child, right? Because in this case, we actually want to include both the children. This is the max through the root, which its parent cannot visit, right? So this is the overall max. And so that's what we'll do here at the bottom. Now, inside our loop, right? So first we need to call the recursive function for the child. So let me go ahead and do that real quick. So the next thing we'll do is in our overall max, we need to make sure that we include the child node info's max as a possible candidate, right? Because the overall max might as well be fully in the child subtree. Now, what we want to do is aggregate the max through root of the child as our in our max child and our second max child, right? Because that's what we'll use to kind of visit or compare the overall max and max child as we discussed earlier. But we only want to do that if the letters are different, right? Because if it's the same, it's not a potential candidate to kind of traverse through. It's still a candidate where we might want to visit because the max could be fully in the child subtree, right? But it's not necessarily a candidate that we'll add to our path for the root, right? So we'll only do this next step if the character at the current node is not equal to the character at the child. So only if this is the case, here we'll consider the child node info's max through root to compute our max child and our second max child. So I've gone ahead and done that here. So here it's just basically an algorithm that says, okay, if the max through root is greater than max, we kind of shift the second max child out, we replace it with max, and we replace our max child with our child's max because that's now the highest number. And otherwise, if it's only greater than the second but not the first max child, then we just replace the second one with the new one, right? And if it's not greater than any of them, we just continue because we're only interested in the top two maxes. So I believe this should do it. Let's try to run the code. Oops, here I have max child. This should be max through root, not max child. Perfect, accepted. Let's submit. Alright, thank you so much for watching. I'll see you in the next video. Cheers. And don't forget to leave me a like or subscribe if you like this content. Thank you.